people can see that. Yeah, I guess I'm not going to be in the way. Cool. Hi, everybody. Glad to be here. I'm in town because we're going to ACCU, and there was a particular art exhibit we wanted to see at a museum here, so we figured why not come to Paris. So how many folks here have written code that runs on a GPU? Well, some of you. How many of you have used CUDA specifically? Yeah. Experience is kind of a little meh. Sometimes it's fun, sometimes it's good, sometimes it's, not great. CUDA is, about 20 years old now, and it's evolved a lot over the time. So, the first version of CUDA, you didn't have functions. You couldn't write functions. Everything had to be inlined. You had basically no abstractions. It's evolved a lot over the years. The thing that hasn't evolved has been how we teach CUDA. And so we've made a big effort this year to rethink how we teach people to program our platform. In particular, we now want to teach people things from high level to low level. So it's like if you're teaching people C++ in a university setting today, you don't start with pointers. You start with high level abstractions. You teach pointers and the low level stuff last. All of the CUDA material, the CUDA education material out there, it starts with the equivalent of pointers. And it's actually worse because it sometimes starts at lower level things than that. So today I'm going to give a talk about how, with the tools, libraries, best practices that you should use when writing CUDA C++ code. Talks about 35, 40 minutes. And if we get through that, we don't have that many questions, I have a bonus 10-minute talk that we can do about some very cool, exciting things. So my name is Bryce Adelstein Lelbach. I am a principal architect at NVIDIA, where I lead programming language design and evolution. So my job is basically to make sure that every major programming language is a GPU programming language. So that's from Fortran to C++ to Rust to JavaScript, maybe even in the future. So I've been involved in the leadership of a number of different programming languages. I chaired the Standard C++ Library Evolution group and the American Programming Languages Standards Committee. All right, so why would we want to run our code on a GPU in the first place? So modern CPUs and GPUs are both general purpose processors that can run almost any kind of code. The G in GPU used to stand for graphics. It used to be largely a fixed function hardware unit. Today, they're really just a different type of general purpose processor, and that's really how you should think about them. They differ, CPUs and GPUs, in what type of workloads they are optimized for. So CPUs are optimized for latency. They have more powerful cores and threads, but they have less of them. And they have less latency to access memory and more memory available to access, but that comes at the cost of much lower throughput. Now, GPUs are optimized for bandwidth and parallelism. So they can run hundreds of thousands of threads. Their memory latency is a bit higher, but their throughput to memory is substantially greater. So how do we program a GPU in C++? Well, we're going to use CUDA C++ and NVIDIA's accelerated libraries. So what exactly is CUDA C++? CUDA C++ is an extension of standard C++ for writing programs that simultaneously run on CPUs, which we call hosts, and GPUs, which we call devices. So in host code, you just write regular C++. You can use all of standard C++ in your host code in isolation. And in device code, you can use most but not all of standard C++. And things like today, you can't throw an exception in device code. You could use virtual classes. You can use some large parts of the standard library. You can do most of the things you'd be able to do in standard C++, but not quite everything. And then there are some restrictions about how host code and device code can interact. So for example, a variable on the stack in device code can't be accessed by host code if you were to pass it by reference. And there's other sorts of little restrictions like that that you need to be aware of. So you don't have to write your CUDA C++ programs from scratch. We have a diverse collection of CUDA accelerated libraries that you can and should leverage. So these libraries have been carefully designed and tuned to provide the speed of light performance for whatever the application is that you're doing. So before you write any CUDA C++ code, you should first check if there is a library that will work for your particular use case. And if there is, then you should try it out and benchmark it. And if it delivers the performance that you need, then you should just use it and don't try to reinvent the wheel. So we have a couple different categories of libraries. These are our math libraries. We also have a bunch of libraries for doing specific things for specific domains, like machine learning or computer vision or computational lithography, quantum computing, quantum chemistry, stuff like that. We have I/O libraries. We have libraries for doing communication. And then we have sort of our core libraries that are just generic parallel programming libraries. That's mostly what we'll be talking about today. So now let's dive in and look at our first example CUDA C++ program. So imagine that we've got a bunch of cups of hot water at different temperatures that are recorded by a thermometer in each cup. And we want to simulate how these cups will cool down. So we'll do this by applying Newton's law of cooling for a number of time steps to the cups. If you see me taking pictures here, it's just because I've noticed a typo in my slide notes and I need to slowly eliminate them over time. So in standard C++, we are going to represent our set of cups with just a std vector of floats. And then next we're going to define our per cup cooling operator with a C++ lambda, which is just a fancy way of defining a function object in modern C++. And then for each time step, we will apply the operator to all of the cups using one of the standard C++ algorithms, std transform, which just takes the operator, applies it to each one of the inputs, and then writes the result to the output. Now, when we compile this standard C++ code, our compiler lowers each function and operation to the appropriate instruction set for the target processor. So like that FMA there will get lowered down to this instruction on ARM. Now, when we're writing a CUDA C++ program, there are at least two different target processors. There's the host and there's the device. And each has its own instruction set. So the CUDA C++ compiler, NVCC, will compile the CUDA C++ code for different targets. But how does NVCC know what target a particular function should be compiled for? Well, that's what execution space annotations are for. So if you don't provide an execution space annotation, then the function will only be compiled for host code. That means the CPU. You can also explicitly request this with the host annotation. And if a function has only the device annotation, then it will be compiled only for the device code, meaning the GPU. And you won't be able to call it from a host code. Now, if a function has both the host and device annotation, then it can be used on both the CPU and the GPU. So now our operator can run on our GPU, but we still need to actually invoke it there. Execution of a CUDA program is always going to begin on the host, and work must be explicitly launched on the device. So transitions between host and device are always going to be explicit. You have to call a function that launches work on the GPU. CUDA C++ will not magically decide to run things on the GPU for you. So functions that are invoked on the device will stay on the device. You can't launch host functions from the device, only vice versa. So going back to our example, the work that we want to launch on the device is our std transform right here. So we can launch this on the device by using thrust transform. And that's going to do the same thing as std transform, except it'll be in parallel, and in this case it will be on the device. In these thrust algorithms, they take an additional parameter, an execution policy, which describes your requirements for how the algorithm can be parallelized. And in this case, we're asking for the algorithm to be launched on parallel on a CUDA device. So if you're familiar with the standard C++ parallel algorithms, they were inspired by thrust. And that design is it's basically the same basic design here. So we also need to make sure that the data is accessible on the device, which we can do by switching from std vector to thrust universal vector. So thrust, this library here, is the C++ parallel algorithm library. Its execution policy algorithms, as I mentioned, were adopted by standard C++ in 2017. So thrust has implementations of those standard parallel algorithms. And it also has a collection of extensions and additions to the standard algorithms. Thrust also has heterogeneous containers that behave like std vector, but store their contents in different kinds of memory that are accessible to different kinds of processors. So std vector's contents might only be accessible in host code. When you construct or assign to a std vector, that operation is going to be done in serial. And that can be quite slow if you're dealing with a large amount of data, as we often do when using GPUs. Now, thrust vectors contents are always accessible, or thrust universal vectors contents are always accessible in both host and device code. And operations on all thrust vectors, like construction and assignment, are executed in parallel on the device or whatever the applicable execution target is. So thrust also has a collection of iterators, of composable iterators, somewhat similar to C++ ranges, that can be used in conjunction with thrust algorithms to compose more complex computational patterns. So standard C++ and thrust algorithms typically iterate over sequences of objects, for example, the elements of a container. But in numerical and scientific computing, we often want to iterate through indices instead of objects. Now we can do this with thrust counting iterators. So a counting iterator is constructed from an integer, and it represents the range of all integers from that integer onwards. So when dereferenced, it's just going to return that integer. And when it's incremented, it just increments that integer. So by passing a counting iterator to a thrust algorithm like for each n, we can iterate over the indices of a container instead of the objects in that container. Thrust also has a constant iterator, which will just repeat the given integer forever. So iterators can help us fuse together operations into beefier and more efficient work. So suppose that we want to transform some data with one function f, and then we want to reduce it with some reduction operation g. So there's two problems with the approach as we've shown right here. By default, the thrust algorithms are fork-join synchronous. So each invocation launches its work on the device and then blocks on the host until that work completes. So in our example, this leads to an unnecessary latency bubble that can degrade performance for us, because we're going to wait on the host for the transform to finish before we start on the reduce, before we've even queued the reduce to the device, even though there's nothing that we need to do on the host with the result of that transform. And additionally, we've had to allocate ON temporary storage for that transformation, which is going to waste precious device memory and cause expensive and unnecessary loads and stores from device to global memory. So one way we can address this problem is to just fuse the operations together into a single parallel invocation, which can be done with a transform iterator. So a transform iterator takes some other iterator and a function, and when you iterate a transform iterator, you get the result of applying the function to the values from that underlying iterator. And this is done completely lazily. So the function is only evaluated as it's needed when the elements of that returned range are accessed. So for example, here, f is not going to be evaluated until the elements of it are accessed in that reduction. So sometimes we need to combine together multiple different inputs into a single range to pass to an algorithm. And we can do this with a zip iterator. So a zip iterator will take any number of other iterators, and it will produce tuples that are a combination of values from the underlying iterators at the corresponding position. So for example, here we make a zip iterator from x and y. So when you dereference this iterator the first time, you're going to get the two-element tuple x of 0, y of 0. And then if we increment it and dereference it again, we'll get x of 1 and y of 1. And there's a cute trick that we can do with this, which is we can use these zip iterators to invoke algorithms on overlapping windows or stencils of elements. So for example, here, we're constructing a zip iterator to the adjacent pairs of elements of x, and then applying the function f to each pair with for each n. So f is going to be invoked with x of 0 and x of 1, and then it will be invoked with x of 1 and x of 2, and then it'll be invoked with x of 2 and x of 3. So if you're familiar with the C++ 20 range adapter adjacent, this is basically Thrust's form of it. So let's look at another example that kind of combines all these ideas together. So suppose that we have two vectors of the same length, a and b, and we want to calculate the maximum difference between corresponding elements of each vector. So we can do this by first calculating the difference between each two pairs of elements, and then doing a max reduction of those differences. So we're going to start off with two thrust universal vectors, a and b, and then we calculate the differences between each two elements of a and b, storing it in a temporary vector that we've created here. And then finally, we do a reduction of the differences with maximum as the reduction operator. And we can improve this by replacing the transform with a zip iterator and a transform iterator. Now we no longer need temporary storage. The zip iterator is just going to produce two-element tuples of each corresponding element of A and B. And then the transform iterator takes that zipped tuple and applies a lambda function to each element that will unpack the tuple and compute the differences between those two values. So this pattern of transforming and then reducing is pretty common, and it's very powerful. So Thrust has a single algorithm called transform reduce that just does this fusion for you with the transform iterator. And it's equivalent to the code that we saw on the slide before. It's actually just implemented in terms of a Thrust transform iterator. So this is known as map reduce in some domains. So we used two new facilities in this example here that I haven't explained yet, which is this CUDA std tuple thing and this CUDA maximum thing. So that's instead of using like std tuple or std max. So these are facilities from libcu++, which is CUDA C++'s foundational and standard library. Unfortunately, I do not have a shirt for libcu++. So CUDA C++ uses your host platform's C++ compiler and C++ standard library for host code. So that's going to be GCC, Clang, MSVC, etc. So the facilities that are in the std namespace come from that host C++ standard library, and they are host only, and we don't want to trample on those. So libcu++ provides a subset of the C++ standard library in the CUDA std namespace. Most of the useful stuff is there, but like, locales and IO streams, aren't. So these facilities can be used in and across host and device code, importantly including a lot of the synchronization facilities in the standard library, like atomics, barriers, semaphores, etc. So libcu++ also has many extensions to the C++ standard library, as well as modern C++ APIs for the CUDA runtime and device-side facilities. And you can find these in the CUDA : namespace. And beta features that are not yet stable are in the CUDA experimental or CUDA X namespace. So now let's take a look at one of the most popular kinds of extended algorithms in Thrust, which is the by-key algorithms. So by-key algorithms will divide the input up into contiguous groups and then invoke the underlying algorithm on each group. So you can also think of them as like batched or segmented algorithms. So for example, suppose that we have a matrix and we want to sum each row. To use a by-key algorithm to solve this problem, we must first create a range of keys that define the groups, which is going to be each row. So each set of consecutive keys that compare equal defines a group. That's certainly a typo. These slides are new. These like 7. So in our example, all the elements in the same row should have the same key. And the value of that key can be its row index. So we don't have to materialize these keys in memory. We can just generate them with thrust lazy iterators. So we use a counting iterator to generate the linearized location of each element. And then we determine its row by dividing by the number of columns using a transform iterator. So next, we'll need some storage for the sums for each row. And we'll just use a universal vector for that. And then we'll invoke our by key algorithm. In this case, we're going to use reduce by key. And so first, the first set of arguments to reduce by key after the execution policy are going to be the keys input, which will just be the thrust lazy iterators that we generated before. And then we'll have our values input, which is just going to be our matrix M here. The underlying algorithm reduce will be applied to the values in each group. Next, we have our keys output. And by key algorithms will copy one key for each group, which is just going to be the first one in the consecutive sequence because they all compared equal. And so it'll copy that one key to the key output range. But in our case, we don't actually need the output keys. They'll just be the same as the index of each sum in the sums vector. So we can use this other thrust iterator, thrust discard iterator, and to just ignore that output. So when you dereference a thrust discard iterator, it returns a special object that just does nothing when it's assigned to. So you can use this to ignore an output to any of these algorithms. And so then finally we have the values output, which will just be our sums vector. And that's it, we're done. We've got our row-wise reduction. So there are a bunch of different by key algorithms in thrust, including reductions, scans, sorts, unique, merge, and then the set operations. And these are particularly useful for batching up operations that you need to perform on different groups of data, and that will allow for a lot more efficient parallel processing. Next slide takes a little while to load because of the animation. So now let's move on to another example working with multidimensional data. Let's simulate my oven, which has a heating element on the top and on the bottom. That is a picture of me from the pandemic, and this is a wonderful apron that one of my interns got me. So we're going to simulate my oven on a 2D grid by solving the heat equation numerically with a 5-point stencil. So our solver function is going to take a thrust execution policy, the dimensions of the grid, and 2 universal vectors, u, which represents the current state, and v, where the next state will be written to. So we'll use a thrust for each n over a counting iterator to implement our stencil. And the for each n lambda will need to capture the grid. However, we can't just capture the universal vectors themselves, because if we captured them by value, we'd end up making a copy, which is not what we want here. And we can't capture them by reference, because while the contents of the universal vectors are accessible on both host and device, the memory that the actual object itself is in may not be accessible in both locations. So instead, we just obtain pointers to the vectors, and then we capture those instead. So the first thing that we're going to do in the body of the lambda is reconstruct the multidimensional indices from the linear index. This is kind of similar to what we did in the example earlier. And next, we need to check if we're in the interior of the grid, in which case we need to apply the stencil. So here's what the stencil computation itself looks like. And then if we're on the boundary, we don't change anything. Now there's a couple different unfortunate things about this code, such as the repetitive and error-prone multidimensional indexing. What we really need here is a proper abstraction for multidimensional data. Fortunately, after 10 years, I finally got one of the standard library. It's called stood MDSpan. And what it is it's a non-owning handle to multidimensional data. So it's basically like a pointer plus metadata. If you're familiar with stood span, it's like that, just in multiple dimensions. So the layout of an MDSpan is configurable, and the dimensions can be specified either at runtime or at compile time. And copying them is cheap and trivial because you just copy the pointer, not the underlying contents. An MDSpan has a powerful slicing facility called sub-MDSpan, which will reproduce new MDSpans that view a subset of the same underlying data. So let's rewrite our heat equation solver to use MDSpans instead. So instead of taking universal vectors and obtaining pointers to them that we capture, we can just take MDSpans, and those can just be captured by value and copied to the device. And we replace the manual indexing with calls to MDSpan's index operator with the multidimensional coordinates. So now let's write a function to set up our initial state. And it's going to take a policy and an MDSpan to initialize. So we need to break the grid down into 3 regions that we need to set. We'll use sub-MDSpan, which is that MDSpan slicing operation, to obtain MDSpans to these 3 regions. So sub-MDSpan takes an MDSpan and then one slice specifier for each dimension. And the slice specifier indicates which indices from that dimension should be selected. So a slice specifier could be a single index, it could be a range of indices, which could optionally have a stride, or it could be the entire dimension, which is indicated by full extent. So the first 2 regions that we need are just the row at the top of the grid and the row at the bottom of the grid. And then the last region is just all of the interior points, so everything except for the first and last row. So we'll use sub-MDSpan, we'll get 3 views into that original MDSpan, and then we'll initialize those. And we'll set the top and the bottom row to a high temperature. We're just using thrust fill in here, which will just fill in that region with a particular value. And then we'll just set the interior region to a lower temperature. So now we'll write the time stepping loop that will repeatedly call the solver. So we're going to output the state of the system periodically during this loop. So after every compute steps evaluations, we'll do 1 output. So in total, we're going to do write steps times compute steps iterations here. So we'll start by setting up our 2 universal vectors u and v and constructing MDSpans to them. And then we'll initialize u with that function that we just wrote. And then next, every write step, we'll save the current state by calling some save to file function on u. And then for every compute step, we'll call our solver function with u as the input and v as the output. And then we'll set the new state from that solve as the input for the next solve by just swapping u and v. Now, as we discussed earlier, thrust algorithms are all fork join synchronous by default. So they launch the device work, and then they wait until that work has completed before they return to the caller. So this introduces unnecessary waiting on the host and underutilization on the device because we can't launch the next piece of work until the first one finishes. So we want to be able to overlap the latency of launching device work, which is relatively high, so that our GPU will always have work in the queue and reach maximum utilization. So that means we need asynchrony, and for that, with thrust, we're going to have to change the execution policy that we're using here. So the thrust CUDA par no sync policy will not wait for device work after it has been launched. The algorithm call will return immediately, and the caller will be responsible for synchronizing later. So in our case, we'll need to wait on all device work every write step before we call save to file to ensure that the last compute step has completed before we begin writing to disk. So this is a good start to making our code asynchronous, and the next step will be to use CUDA streams. So a stream is a chain of device work that is executed in order. You can think of it kind of like a queue. So you can have thrust launch work on a specific stream by passing the stream to the on method of the execution policy. So here we asynchronously launch a for each applying F and a for each applying G on the device. So the F for each will complete execution before the G for each starts. So a stream can record an event that host code can synchronize with, waiting for all work up until that event to complete. And you can do this in code by simply calling wait on the stream object, which will implicitly record an event. And in this case, it'll wait for both for eaches to complete. But if we instead wait before the call to the G for each, then we're going to only wait for the F for each, even if that G for each was added to the stream by some other thread. You can create multiple streams that will run concurrently on a single device, just as you can run multiple threads concurrently on a single CPU. And streams can wait upon other streams through events. So you can explicitly record an event on one stream with the record event method, and then you can have another stream wait for that event by calling the overload of wait on a stream that takes an event. Now, note that the host will not block on the event when you call this particular overload of wait. It will just tell the stream to block on the event. It's a little bit confusing that both of these things have the same name of wait. I've told the engineering team that they should probably change that before they remove the X from the experimental part of this. So you can use streams to control what specific device your code runs on. So by default, they're going to be constructed on the first device, but you can explicitly construct them on any device in your system. And dependencies can be established between streams running on different devices. So let's revisit that heat equation example and add streams. So we're going to create a stream, and then we're going to define an asynchronous policy that will run on that stream, and then we'll use that policy in all of our calls to thrust. And instead of waiting with all work on the device at the start of each write step, we'll just wait for the work on our stream. Now there are some limits to thrust's support for asynchrony. It works great for algorithms like for each and transform, but some thrust algorithms either return a result that depends on the computation or they allocate temporary storage for the computation. And today, these interfaces will always block even with the par no sync policy. So for example, consider inclusive scan. It returns an iterator to the end of the output. This doesn't depend on the computation, so we can just compute it beforehand by incrementing the output iterator by the size of the input. Thrust assumes you've always got a random access iterator, so it's fine to do that. However, unlike for each and transform, scan algorithms require temporary storage, and thrust has to allocate and deallocate this storage before the algorithm returns, and the deallocation of that storage will block today, even with the par no sync policy. And I rarely write PRs, but this bothers me so much that I wrote a PR to fix this because we do have an async allocate and deallocate thing. So check back in like 2 weeks, and this restriction at least will probably be gone. More problematic is algorithms like copyIf that return an iterator to the end of the output. In the case of copyIf, that iterator depends on how many elements pass the predicate, and we won't know that until the computation is complete. And so these kinds of algorithms are implemented in terms of a scan, so they also need temporary storage. So we can solve that problem, but we can't solve the problem that the thing that this returns, we have to wait for the computation to complete before we return it. So thrust has to block before returning from these algorithms, even with the par no sync policy. And reduction-based algorithms like reduce, count, findIf, and max element return the result of the reduction, which also requires blocking, and they also need to allocate temporary storage. So we have a plan where we just add new versions of these, like a reduce into, where it takes an iterator, an output iterator, to write the result to and just returns void. So those are coming down the pipeline. But if we need asynchronous versions of these algorithms today, there's another slightly lower level CUDA C++ algorithms library that we can use that is built from the ground up to be asynchronous. And that library is cub, which is the CUDA C++ algorithm authoring toolkit. So cub provides cooperative building blocks for writing your own device-side parallel algorithms. That's sort of the primary thing it's used for, but that's not really the focus of our talk today. If anything, we want to discourage you writing CUDA kernels yourselves. But if you're interested in that, there was a really great talk at NVIDIA's GTC conference this year, which was 2 weeks ago, about writing CUDA C++ kernels in a modern and idiomatic C++ fashion. There's a link to it there, and there will be a link in the last slide too. So CUB also exposes device-wide algorithms that you launch from the host, just like Thrust, and that's the part of CUB that we're going to talk about today. So as I said, CUB is a little bit lower level than Thrust. So we just discussed how some Thrust algorithms need to allocate temporary storage, like reductions. So we implement GPU reductions with 2 passes. The first pass divides the input up into chunks, each of which is handled by a block of threads, which will collectively reduce that entire chunk to a single value. And then that gets stored in a temporary array. And then a second pass will use a single block of threads to reduce all of those aggregates in the temporary array to a single result. So with Thrust, the temporary array allocation and deallocation is done implicitly within the algorithm. CUB is asynchronous by design, so it doesn't return the reduction result by value. Instead, it takes an iterator, and then it assigns the reduction result to that iterator. So when we call a CUB reduction, we need some device-accessible storage for that result. So we'll just create a universal vector for that. And with CUB today, we must allocate the temporary storage explicitly. But first, we need to determine how much temporary storage we'll need. And this is not trivial to figure out because it will depend upon the algorithm that we're calling, the data type, the operators, the device architecture, some like weird table of like heuristic tuning parameters. And so since you need all the same information that you'd invoke the algorithm with to compute the temporary storage size, the way that you do that is we just use the same interface to do both. So the first 2 parameters to CUB algorithms are a pointer to temporary storage and then a reference to the temporary storage size. And if the pointer to temporary storage is null, then the algorithm will not actually be invoked, but instead it will compute the temporary storage size and it will assign it to that integral reference that you passed in. No, it's not me. Sounded like mine. So next we need to allocate the temporary storage, and we can do this with a thrust vector of CUDA std bytes. And finally, we call the CUB algorithm again, and this time we pass in a non-null pointer to the temporary storage, and the work will be asynchronously launched on the device this time. So let's rewrite our heat equation solver from before to use CUB. So CUB has a for each algorithm just like Thrust. And since this one never needs temporary storage, you don't need to pass in a temporary storage pointer or size. And CUB algorithms don't take execution policies, so we don't need to pass that in anymore. But we can specify what stream to run on with CUB. It's going to always be the last argument to a CUB algorithm, so we just pass in the stream directly instead. And we use this CUDA X stream ref, which is like a non-owning handle to a stream object that's part of libcu++. So we're still using a counting iterator here. Thrust iterators work great with CUB, and it's pretty common for people to use them together. But CUB has a better algorithm for this particular use case of iterating an MD span, which is for each in extents. And this takes an MD span's extents object instead of an iterator and calls the operator with the multidimensional indices. The extents object describes the shape of that multidimensional data. And so then you don't have to reconstruct the multidimensional indexing yourself, which reduces complexity and also increases performance because CUB will do that reconstruction for you in the fastest way possible. So we're going to add a for each extents algorithm to Thrust too. That's in the works. And we're going to probably propose some form of this to the C++ standard library to make it easier to work with multidimensional data. In particular because std span does not expose iterators because multidimensional iterators have a number of performance problems on CPUs, like they seriously inhibit vectorization. So we decided not to add that performance foot gun. But that means it's kind of annoying to use MD-span with standard C++ algorithms. So we want to just add a simple way to be able to iterate through an MD-span to standard C++. So last topic. Throughout this talk, we've been using Thrust Universal Vector for device accessible storage. And universal vectors are implemented with CUDA unified memory. So let's go into the hood and see how that actually works. So a universal vector, I said, is accessible from both host code and device code. But the host and device, in most cases, have different physical memory. Some cases, like an embedded platform, they may have the same physical memory. But just assume, conceptually, that they're in two different separate physical memory spaces. So where do the contents of the universal vector actually reside? So thrust universal vector's contents will start on the device, because the way that unified memory works is first touch, and thrust universal vectors will always initialize the data on the device. And then if we access an element of the vector from the host, the CUDA platform may have to migrate the data from the device to the host. And by the platform, I mean a combination of the runtime and like the kernel driver. And the mechanisms for this transfer will vary between systems. On systems with an NVIDIA CPU and a GPU, there may not be a migration at all, or the migration may be done by hardware facilities, or it may be done through page table access by just paging the memory between CPU and GPU. Migrations won't move the entire vector. They'll move just a part of it. And it won't be at the granularity of a single element, though. Chunks will be migrated at a time. It's also worth mentioning on some platforms, if the CPU and the GPU do share the same memory space, then a migration would not actually need to occur at all. Now, if there is a migration, then we end up with two copies of that element that are resident in memory, and any other elements that were speculatively migrated. So there's going to be a copy in host memory, and then we have this stale copy in device memory. And if we access a different part of the vector later, then it will trigger another migration. And if we later access that first element from device code, well, then we need to migrate the element back. So the point here is that with CUDA unified memory, the transfers are implicit and piecemeal. And this has a number of advantages. It's a lot simpler to program, first of all. And that's why we start off with it. And it also allows you to oversubscribe GPU memory. Because if you have a universal vector that is too large to fit into GPU memory, that's perfectly fine. If the GPU runs out of memory, it'll just page stuff out. And so as long as the window of what you're accessing is like reasonable, you'll still be able to work with it. And if we're not the other problem with unified memory is that if we're not accessing, or sorry, another advantage of unified memory is that if we're not accessing the entire contents, we have like a really big universal vector, but we're sparsely accessing it on the GPU, it might be more efficient to use unified memory instead of doing a copy of the entire vector, because if we're doing a copy of the entire vector and we're not actually accessing everything, then we're just wasting device memory. But if we're iterating through the entire vector, it will be less performant to migrate the vector piece by piece instead of doing it all at once on some platforms. And so unified memory is only one of the options that are available to us. As I said, it's the most user-friendly, and that's why we start with it. But we can also allocate memory that is tied to a particular target. So host vector will allocate memory that can only be accessed in host code. It's just like std vector. And device vector will allocate memory that can only be accessed in device code. And we actually saw that once because we used thrust device vector to allocate the temporary storage for the cub reduction earlier, because we never need to touch that in the host. There's no reason to put that into unified memory. To transfer between memory spaces, we can just use thrust copy, which works just like std copy, but unlike std copy, thrust copy understands different memory spaces and the various ways of moving memory between them, and it will dispatch to the correct and most optimal mechanism possible. So it'll look at like, what are the data types? Is this a trivially copyable type? Where does this memory live? What are the capabilities of the hardware? There's all sorts of hardware memory transfer engines that can be used to avoid having to do a copy that actually does use compute resources and just implicitly in the background transfers things. It's very clever. You should just use that instead of trying to figure it out yourself. So if we take a look again at our heat equation code, our save to file function is going to access that entire U vector on the host. And that's going to be inefficient. So instead, we can create a staging buffer in host-only memory. And then we can explicitly copy from our problem state in device memory to the host staging memory buffer with a thrust copy. And so now not only is our memory transfer more efficient, but we're also able to overlap the compute with the I/O. So our code will first initialize the problem state asynchronously on the device. And then next, we're going to enter that outer write loop on the host. And then every write step, we start by copying U to buff. And then we immediately wait on the stream, ensuring any previous compute and the copy have completed before we continue. And then next, we asynchronously launch our heat equation solver compute step times on our stream. And then on the host, we start outputting the staging buffer at the same time as the heat equation solves are happening on the GPU. And then we just repeat this for every iteration of the outer write loop. All right, so we've only talked about a couple of the CUDA accelerated libraries today, thrust, cub, and libcu++. But there's many more to explore. There's math libraries, there's machine learning libraries, data science libraries, simulation, physics, I/O networking, and then various device-side programming libraries. And if you want to learn more about what is available in CUDA programming in general, we have a whole track of CUDA developer content at GTC, which is NVIDIA's developer conference, happened about 2 weeks ago. There's a bunch of different interesting sessions. The one that's probably most interesting to this audience is there was a session that talked about how to write CUDA C++ kernels, which is going to taking this talk a little bit step further, looking at how do we go and do the more advanced thing. And then there's also a corresponding version of this talk for Python and a corresponding version of the kernel talk for Python. And we've also launched a whole new CUDA curriculum with tutorials, notebooks, and other learning materials, some of which is an expansion of this talk. And you can find all of that. It's all open source on our Accelerated Computing Hub on GitHub. So it's a bunch of Jupyter notebooks and then slides that walk you through them. And we'll also be teaching some of those tutorials at various conferences this year. And I should acknowledge all my colleagues who are behind all of the technologies that we've covered today. When I started back at NVIDIA in 2017, which feels like a very long time ago, and when I founded the CUDA C++ core libraries team, I was really one of the only people working on modern C++ exposure for CUDA. But now we've got a whole team of like 15 people working on this, led by two really great managers, Jake Himstad and Georgy Evtushenko. So there's a lot of really great resources and recent developers out there. So that is it for this talk. My thingy says we are at 45-ish minutes. So let's take some questions, and then I will check with the organizers whether we can do the other little bonus talk, which would take like maybe 10 minutes, but I don't want to keep people from food. So questions? Yeah.
When you use a thrust pulse vector, is it allocated using CUDA's allocator, or is it the regular malloc?
When you allocate a thrust host vector, which allocator does it use? Pretty sure it just uses malloc and free, or I think it uses like new and free. Like it doesn't use a CUDA allocation pipeline, I believe. Yeah.
So is there a way using thrust to get pin memory?
Yeah, so we have, that's a good question, and the tutorial that's a more expanded version of this takes this example and adds another staging buffer, because one of the problem with this example is that the device to host copy that we're doing here is expensive. And it's actually going to be slower than all the compute that we do. So what you actually want to do is you want to have two buffers. You want to have one buffer on the device, and you copy the device buffer first, then you let the compute continue, and then you asynchronously copy from the device buffer to the host buffer. And for that sort of copy, from a device buffer from device to host, the most efficient way to do that is with what's called host-pinned memory. So that is memory that is locked in so that it won't be ever paged out. Because if you have memory that could be paged, then the CUDA memory copy engine can't use that. It has to create its own little buffer internally of page-locked memory and copy to there. And so you get a much slower memory copy. So all those sorts of techniques and how you can use host-pinned memory with thrust, which is just spelled thrust universal host pinned vector. That's covered in the tutorial, which is linked here. And will probably be covered in a longer version of this talk that I'll give at some point.
Thank you.
Yeah.
Not using the pin memory also prevents kernel executing while you are copying, right?
Not using pin memory also prevents kernels executing while you're copying. Yeah, in some cases, yeah. So yeah, generally, if you're copying from device memory to host memory, the fastest way to do it is to make sure that the host memory is going to be pinned. And you can do that by just, there's an API you can call to say, hey, here's my host memory, please pin it and lock it. Or you can just use an abstraction like thrust universal host pin memory, where it'll do the allocation and set up the pinning for you.
But what would be nice is an asynchronous API for pin memory allocation.
Asynchronous API for pin memory allocation. Yeah, that would be nice. I don't know whether we have a form of that. I don't know whether that's a part of the async memory allocation. I'll put it on my, my to-do list, which is async host pinned memory allocation. To some degree there we may have, I actually think that it's almost certainly possible to do that. It's a little complicated because the way that you actually allocate the host pin memory is you just allocate regular memory and then you tell the OS to lock it. There's an async memmap, CUDA memmap API that might do what you want though. So you may want to check that out.
HMM, right?
I don't know that, yeah, that may require HMM, yeah. Okay, any other questions here?
Yeah, online. How do you compare CUDA to OpenCL or other similar options?
So OpenCL is more of a C-style interface. The better comparison is to SYCL. The way I would think about that comparison is that SYCL is like, SYCL is comparable to like CUDA circa like 2015, where SYCL is a much, it reflects a much earlier GPU programming model where GPUs were a lot less capable and where you had to be a lot more explicit about things. And SYCL doesn't, or it hasn't until recently had capabilities like unified memory and doesn't have capabilities like independent threads, which gives you forward progress guarantees and synchronization guarantees that you get with CUDA. So I think SYCL is a little bit outdated in terms of how it presents the GPU to you. It presents the GPU as this exotic accelerator thing, and we want you to think more about the GPU as just a general purpose processor. SYCL is also fairly deeply tied to the Intel ecosystem, whereas CUDA is specific to the NVIDIA ecosystem. So if you're programming an Intel GPU, you probably want to use SYCL. I don't know many people have Intel GPUs that want to program. So if you want to program an NVIDIA GPU, you should use CUDA. Yeah, other questions?
Yeah, from Clément, coming from the rendering world, I'm used to shaders and dispatch code for compute works. Each dispatch may require fences on the GPU side for synchro. Is there any work to rely on those with Thrust?
So you don't have to do those sorts of synchronizations explicitly, but if you have CPU threads that are talking to GPU threads, then yes, you need to synchronize. GPU threads implement the C++ memory model. So the way that you should synchronize between CPU and GPU threads is the same way that you'd synchronize between CPU threads, which is using the C++ memory model, using atomics or using concurrency primitives. You'll need to use the ones that are in libcu++. The libcu++ synchronization primitives have an additional parameter called a thread scope. And the default thread scope is system-wide, which is the model in C++, which is that these two threads that are synchronizing in atomic, it could be any two threads in the system. But there are other thread scopes, like a thread scope device, which is just for things synchronizing within the device, or a thread scope block, which is just for things synchronizing within one block of threads that are slightly more efficient. But yeah, the best model for synchronizing between CPU and GPU memory is going to be to use just the C++ synchronization primitives that you know today. A lot of them, the new ones like barrier and semaphore, were proposed by folks working at NVIDIA. They're specifically designed to be really good for high concurrency situations like GPUs. All right, any other questions?
it feels like with CUDA I can write code that works on the device, but unless I'm very aware of the GPU architecture, I might unknowingly write highly inefficient code. Would you agree?
With Thrust, that's less likely. If you're writing raw CUDA C++, that is certainly true, that it is getting harder and harder to program GPUs. The second bonus talk I have will cover that a little bit. But the accelerated libraries are all, fairly tuned and optimized by ninjas. And so if you're using accelerated libraries, you're probably going to get pretty good performance. And if you aren't getting good performance, it's usually just because you're using a library like Thrust that is by default synchronous. Like the kernels aren't going to be slow. It's going to be the synchronization or things like that that would be slow. Yeah. Any other questions?